Matter and medium. Matter cannot be considered in isolation, but must be considered as part of its own environment. Defining the medium is complex. On the one hand, we must consider the problem of space and its content, on the other hand, the problem of matter and energy, and on the other hand, that of time and inertia. Given a matter is positioned in a space, surrounded by other matter, immersed in energy fields that exert forces on such matter and exposed to a future that manifests itself with inertial effects from the changes that occur in the environment and as they propagate towards the location of the matter, either by the propagation of waves or by the displacement of other matter in space. We will consider a configuration of matter in three possible environments. In interstellar space, far from any stars and all other prominent matter. On the Earth's surface, subject to the Earth's gravitational field. Within the Earth, subject to both the remaining terrestrial gravitational field and the pressure of the matter that is located above the location of the matter considered. Let us consider the case of empty space where there may be some grouping of atoms in the form of ions, gaseous plasma. In such conditions we will not find an atom in isolation, but rather it will be found together with other atoms. We can assume that such a gaseous conformation may be the result of the explosion of some supernova and that such groupings of atoms were distributed in space. If we consider such a group in isolation, it will be exposed to the temperature of the zero level, cosmic background radiation, which is 2.725 Kelvin. That is to say that such atoms will not be at absolute zero but at about minus 270 degrees centigrade, which means that such atoms have a certain level of thermal activity between them, which will add to the gravitational effect of the masses of the atoms, but since they are ions, in reality the force of cohesion between that group will be the resulting electromagnetic force of the whole. This is the most isolated condition of matter that we can consider. Now, under normal conditions, such a group will be immersed in different electromagnetic fields of nearby stars or other nearby objects, which will generate additional forces on said group. And finally we must consider the effects of nearby gravitational forces, much weaker than the forces we previously mentioned, but which could contribute something to the movement of the whole. All of this is what we call the environment or environment in which the grouping of matter is inserted. We can consider another example of matter, but on a planet, say the Earth. Now the situation is much more complex, because even considering an object or group of atoms that is on the Earth's surface, we must consider the following additional factors. That object will be exposed to the pressure of the atmosphere, 1 atmosphere or 101,325 pascals, approximately, depending on its altitude and atmospheric conditions of the day. It will be exposed to the ambient temperature, which may vary from minus 20 degrees to 40 degrees centigrade, depending on the season of the year. We can consider the ambient temperature as 300 Kelvin, about 27 degrees centigrade. And to all local conditions, Earth's magnetic field at that location, Earth's gravitational field at that location, the effect of the remaining Earth matter, electromagnetic fields present, radio waves and other radiation, such as cosmic rays, etc. We then see that a simple object or a simple group of atoms is exposed to a very broad environment to be considered separate or isolated. A third case is to consider the object inside the Earth, which will be exposed to a certain pressure, several atmospheres, depending on the depth at which it is located. At a certain temperature, several hundred or even thousands of degrees, and the local conditions of magnetism, gravity and other disturbances, to which it is exposed. Here we have only considered gravity and electromagnetism since the strong and weak nuclear forces only act at the scale of the atomic nucleus, therefore, it is an internal effect of each atom and does not affect adjacent atoms or other more distant atoms. We speak of forces when we consider the effect at a particular point or position in space, while we speak of a force field when we consider the distributed effect that affects the entire space or environment of the space that we will consider as the environment for the object. A particular case is that of waves, which are fields in motion due to some fluctuation that has occurred in the force field and that propagate in space. All the mentioned factors influence the properties and state of the atoms, or looking at it from another perspective, the atoms are sensitive to all the factors that we have listed. That is, the atoms behave as sensors of how reality affects its surrounding environment. That is the atom the constituent of matter, or is the atom the sensor of the state of space at a given location in space? The atom registers the effects of the gravitational field and the electromagnetic fields that surround it. At the moment the gravitational field is unique, and its combined effect at each point in space is considered. On the other hand, the electromagnetic field is multiple and we must consider the effects independently. The change in focus is due to the frequency range of the electromagnetic field, while in the gravitational field, since there are no waves, it lacks frequencies. We have commented in the previous topic about the problems for detecting a gravitational wave, but the gravitational wave implies a fluctuation in some mass, which in some way implies that something has exploded. Such events occur very rarely in the universe. ChatGPT gives an estimate of one supernova explosion every 50 years, considering the average lifetime of stars and the density of stars in the Milky Way. On the other hand, electronic fluctuations in atoms produce electromagnetic waves with a wide range of frequencies, which we will study in Module 2, from frequencies less than 1 Hz to frequencies greater than 300 QHz, kHz, with 1 ZeV zeta eV of energy. Higher frequencies can hardly exist, due to the energy levels involved, but the wavelength for the mentioned frequency is quectometers, 31033, and the Planck distance is in the order of 10 to 35, that is, still shorter wavelengths could exist, implying higher frequencies with even higher energies. We have the electronics to tune and listen to each of these frequencies, which allows us to separate and consider each of the electromagnetic effects independently. The environment surrounding an atom sets the temperature and pressure to which it is exposed. Temperature manifests itself in the activity level of both the atomic nucleus and the surrounding electrons. An atom at 0 degrees Kelvin, absolute zero, is at its minimum level of activity, with its nucleus in a state of rest, its electrons located at the minimum energy levels and the nearby atoms located at the shortest possible distance, if it is a gas, or without electronic activity additional to the structural one, for liquids and solids. It is at the lowest level of activity possible for an atom. Any temperature level above 0 Kelvin implies that the atom is excited, that is, it has a higher level of activity, due to the effect of temperature. Its nucleus begins to vibrate, internal interactions occur in the nucleus, and the electrons have enough energy to move into orbits with levels higher than the minimum. The higher the temperature, the higher the activity level of the atom, and it may lose its valence electrons, matter burns. Pressure is manifested through the compression of atoms, gas, liquid, solid. In the solid state the atoms are located at close distances from each other, to make it a solid, but not necessarily at the shortest possible distance, which is only achieved in a crystalline structure. The range of pressure variation that atoms can withstand with a crystalline structure is very wide. For example, the water at the maximum depth detected, the Mariana Trench, is at a pressure of more than 1,000 atmospheres, and still remains in a liquid state. In the same way, the Earth's mantle, which begins at a depth of 25 to 70 kilometers, remains solid as rock. Higher pressures and temperatures must be reached for the compression state to alter the usual properties of the atoms. In the graph we have illustrated 4 situations that represent the same grouping of matter. It is illustrated how the set of atoms is exposed to both the gravitational and electromagnetic fields, external to the set of matter. The first 3 illustrations represent the situation with the same temperature, but with the set of matter exposed to different levels of pressure, which bring the atoms closer together until the atoms are located at the smallest possible distance in a crystalline structure. The fourth illustration represents the same situation as the first illustration, but with a higher temperature, which increases the internal activity level of the atoms, but not their proximity due to compression. Levels of energy. There is another way to consider the previous problem, and it is from the energy approach. Each location in space, whether in interstellar space or in a planetary location, is at a certain energy level at a certain moment in time, which implies that its environment is fixed by that energy level. It is dependent of that average. For example, if we consider the temperature, say 30 degrees Celsius, you will not be able to change that value instantly to reach, say, 0 degrees Celsius, but to reach the other value it will take an amount of time that depends on the conditions in order to dissipate the temperature. Energy of the object. Examples. If I have boiling water in a jug and I expose it to room temperature, it will take time for the water to reach the value of the room temperature, which will depend on the value of the room temperature 30 degrees, 20 degrees, 10 degrees, 0 degrees, and the possibilities of the boiling water being exposed to air current that allow it to dissipate its heat more quickly. The reverse case is for a block of ice left exposed to ambient temperature, which will melt sooner or later depending on whether the ambient temperature is 0 degrees, 10 degrees, 20 degrees, 30 degrees, or 40 degrees. In the case of the ice block, heat is not dissipated, but heat is gained or accumulated at the expense of the environment. The environment will cool down a little. Thermal inertia depends on both internal factors of the matter, such as the internal properties of the object's structure, caloric coefficient, and the amount of mass of the object, as well as external factors, the environment, such as the energy average at which the object is located and other external conditions such as air currents, etc. Changes in space and matter are not instantaneous, they take time based on a coefficient of inertia. Inertia depends on both internal factors of the matter and the external conditions of the environment or surrounding medium in which the matter is found. With the passage of time, equilibrium is reached, which in the thermal case translates into reaching the average energy of the surrounding environment, and in the case of displacement it will be the momentum of the set of matter, whether at rest or with a certain level of movement, that is, a certain speed. Every change in inertia manifests itself as an acceleration, which, as we know, changes the internal structure of matter, which we experience when there is a sudden change in acceleration that translates into a force. Dissipative, cumulative systems and dynamic equilibrium. We have mentioned that objects tend to balance with their surrounding environment, which is valid for systems or objects that are in an infinite environment. That is, much larger than the object or system being considered. They are usually called open systems, since they allow an exchange of matter and/or energy without limitations. On the other hand, systems that are called closed have a limited amount of either matter and/or energy. In such systems, dynamic balances are required to be maintained over time, which usually imply cycles of repeated fluctuations. We will then analyze the case of the terrestrial climate. In such conditions, the equilibrium is not unique, but rather has a set of phases and is dynamic. That is, the system must go through several or all phases, maintaining long-term balance, which usually generates short-term imbalances, usually located in different regions of the system. In conclusion, we must postulate that matter must be considered as part of the surrounding medium in which it is found and determine whether the surrounding medium is a medium of open exchange or closed exchange, whether dissipative or cumulative. A closed medium of exchange may have a final equilibrium, or an open medium of exchange must generate a dynamic equilibrium system with different phases with successive imbalances. One imbalance will compensate for another in a succession with different successive phases. The problem is more complex when instead of considering a specific object we must consider a larger environment, for which we will illustrate the mechanics of climate, in which we must consider the problem of entropy, structures and exchange. When we have an infinite environment, energy is dissipated or accumulated punctually. We have illustrated this with boiling water and the block of ice. And we consider an infinite environment when the environment is very large with respect to the specific object, 1,000 times or more, for example a jug or a block of ice. When we have a finite environment, energy exchange processes are generated that produce specific patterns or structures of dissipation, accumulation or exchange. The case of the terrestrial climate is the example, since the Earth is of the same order, in size, as the atmospheric mass that intervenes in the climatic process. Something similar happens with the oceans and marine currents. Such processes or structures are those that emerge from the overall situation, since the energy level changes in value until it reaches a level in which dissipative structures are self-generated that keep the whole within a certain dynamic equilibrium. In the case of the Earth's climate, the air in the atmosphere, plus water vapor, intervenes from the energy that arrives from the sun every day, producing asymmetric heating of the Earth's surface. Warming up that, at least, we can divide into 4 sectors. The hemisphere that is in summer and the one that is in winter, plus the portion that is in darkness, night, and the portion that is exposed to warming at that time, day. The most homogeneous case is when the hemispheres are around the equinoxes and the hemispheres are in autumn-spring, with a similar energy distribution in both hemispheres. If we consider the situation described, in principle 2 climatic cells would form, one in the northern hemisphere and the other in the south, but in addition, we must consider the spin of the Earth, which generates 3 climate cells per hemisphere, generating a total of 6 cells on the planet. The cells are formed because the hot air from the equator must move and dissipate towards the cold air at the poles, and vice versa. The cold air must move towards the Earth's equator. The climatic cells are the polar poles, one in each hemisphere, which disperse cold air from the poles, accumulating energy along the way. The Hadleys, one in each hemisphere, which dissipate heat from the equator towards the poles, cooling the equatorial air. The Farrell cells, one in each hemisphere, which are fed from the previous 2 with air of intermediate temperature, balance the imbalances between the polar and Hadley cells, approximately between 30 degrees and 60 degrees latitude. In addition, warm transverse air currents occur near the equator in the east to west direction and cold or temperate currents near 30 degrees latitude that move in a west to east direction. The air rotates to the right, clockwise, in the northern hemisphere and rotates to the left, counterclockwise, in the southern hemisphere. With this dynamic balance, the Earth's climate is maintained at constant values, between -40 degrees to 40 degrees Celsius, which, appropriately, are suitable for life.